Well, good afternoon, good morning, good evening, depending on what time zone you're in. Welcome to the second day of the IWAM symposium from the Thomas Young Center. So yesterday we had a number of really excellent talks on charge transport. My name is Troy Van Voris, and I'll be chairing the session this morning. We'll be hearing a lot about excited state processes. So we have some wonderful talks and some more posters today. And so I will hand the floor over to Weitao Yang from Duke University, our first speaker, who will be telling us about photoemission and photoexcitation spectroscopy from ground state density functional calculations. Take it away, Weitao.
Okay, thank you, Troy. I'd like to thank Joachim and then other organizers for the kind invitation to participate in this really very interesting symposium. I have listened to all the talks and then I really enjoy the symposium. So what I want to talk to you today is about more, not so much on the process, but on the underlying electronic structure theory for describing charge transfer or interface process. And for that, we focus on two spectroscopy, photoemission and photoexcitation spectroscopy. And these are the properties that you would always measure on systems when you want to, the first thing you measure on a system, and how theory predict these properties. So I'll come to the issue using density functional theory, the systematic errors that we can understand it from theoretical analysis, and the correction on those errors using localized orbital scaling correction. And then I talk about how is the density functional theory ground state calculation just remain in a ground state constant calculation with the input functional can achieve a very good description of photoemission and photoexcitation properties. And also relating to the content of the symposium is the charge transfer. So charge transfer systems has one of the biggest challenges, energy level alignment and the density distributions. And I'll tell you what are the challenges and what we can do. Photoemission. So this is a very classical example of spectroscopy, shining light on a material or a molecule and detect the energy, and that's you get the resolution at what electron come out at a particular energy, and that's the photoemission spectrum. Photoexcitation, of course, is very, very familiar to most of us. You excite in a molecule, excite from occupied to unoccupied orbital and create an electron hole pair, or in solids, very similar, but you generate electron from bands. So photoemission spectroscopy actually can be obtained from orbital theory in the very beginning of electronic structure theory. So Hartree-Fock theory, there's already very important conclusion about the orbital energy in Hartree-Fock theory. And then more advanced, of course, the green function theory, that's exactly the right theory to many-body theory to describe photoemission spectrum. And then DFT, and I will tell you what we can do about DFT. So Hartree-Fock theory is the Kupperman theorem that when you freeze all your orbitals, so this is taking a picture from the very good book from Szabo and Osterlund. Taking an electron from a N-electron system with N-1, but you freeze the orbital and calculate the difference between these two states, that's the ionization energy, and then the answer is the orbital energy that you take out with the assumption that frozen orbital approximation. So if you use frozen orbital approximation under the Hartree-Fock approximation, and that's the Kupperman theorem. So the ionization energy is equal negative to orbital energy. For Green's function theory is the Dyson equation for quasi-particles, and this is an equation with non-local potential and non-local energy dependence. Then the eigenvalues out of this is the quasi-particle energy. It's energy of adding electron to the excited states or ground state, and the energy of taking out one electron. So quasi-particle or quasi-holes. So you can this equation, the quantizing equation, can be viewed as really the true theory, and Hartree-Fock approximation is just a simple approximation of using exchange energy to approximate the self-energy, and then the Koopman theorem make really good sense in this perspective. And there's very common used state-of-art GW approximation, which I'm not going to go into details. For DFT, you have very different set of equations. Concept equation, that's your regular concept equation of potential that local, but not energy dependent, or generalized concept, the potential that is non-local and then not energy dependent either. So, so the eigenvalues, the concept eigenvalue or the general concept eigenvalue, what are the meaning? Can they be related to ionization energy? So what do we know about the orbital energy meaning? There is a classical result of Janak that the orbital energy is the derivative of energy with respect to occupation number. This is called Janak theorem. That's on concept eigenvalues. And this is very interesting interpretation, but in no way connect to experiment. This is not an interpretation of physical meaning. It's just a mathematical meaning of what the orbital energy. Then there is also, based on asymptotic analysis, you assume the constant density is exact, and the density has to behave asymptotically for finite system exponentially, and then that maximum eigenvalue of constant it has to relate to the eigenvalue of to minus of ionization energy. So based on asymptotic analysis alone, this can be concluded for the exact constant theory. So there's also very important theoretical work of Purdue, Parr, Levy, Bowditch, that density functional theory for fractional number of electrons. So in this results is that it's a grand canonical ensemble for finite number of particles, but at zero temperature. So in this ensemble argument, the conclusion is that you can have fractional number of electrons, but the energy is a linear line between the integers, between nearby integers. So this is not necessarily directly or not easily directly connect to the states that we're looking at. When we look at states, we don't have to look at ensemble. It's a pure state. So the fractional system, however, the connection have been made to that the fractional number electron condition is closely related. It can be derived based on quantum mechanics of degeneracy. So what does that mean? So if we have two states that have the same energy but two different wave functions, then a linear combination of these two states has the same, satisfy the same Schrodinger equation with the same energy. That is really the linearity of Schrodinger equation, and it's a very profound quantum mechanical conclusion for degenerate states. You can have linear combination of wave function, degenerate wave function at the states. So what it has been developed based on this degeneracy is that the conclusion can be derived for fractional electron exactly based on this. And this was in a paper in 2000. So that we published. When you consider the simple case of hydrogen molecular ion, two protons with one electron. So this proton and this at dissociation limit. So we can have a proton at position A, proton B with electron associated bind to B, or you can have a degenerate solution that electron bound to A. And these two are separate by infinity, so that they're degenerate. You can linear combine these two answers to get the third state, and the wave function is just a sum, and the energy is identical. But in the electron density, something dramatic happened. The electron density of the system is half electron with A and half electron with B, and they are separate by infinity. So the energy of these two halves are additive because they separate infinity, and therefore you have to define the half electron. So this is really the fractional electron comes from the degeneracy of quantum mechanics. It's not from ensemble. It doesn't have to come from ensemble. Come from the degeneracy requirement. And of course, the size consistency requirement. The energy of two separate systems is the sum of the two, because there can't be any physical interactions. So this half electron energy and half electron energy add together is the same as one electron. And therefore, energy of half electron is half energy of one electron. And this is exactly here in the middle, the half electron energy right here. So we have just derived this middle point, and the discussion can extend to any fractional number of electrons, any number of electrons. So the linear condition is a quantum mechanics degeneracy principle requirement. So the conclusion from the linear condition is that you can take since it is energy defined for fractional number of electrons, you can calculate the derivative of energy with respect to the fraction, and because it's two linear line, will be just the two finite difference, and there will be ionization energy or electron affinity, and this is the chemical potential. This is the thermodynamic definition of chemical potential at a zero temperature. So of course there are two, because it's not continuous. So you have a left derivative and a right derivative that will give you I and A. So the chemical potential is related to I and A, but how to calculate chemical potential from a ground state DFT calculation was not known until 2008. So in 2008, we derived the formula to calculate chemical potential. This is I'm not going to any details, but that's the conclusion. The result is that the chemical potential equal to the derivative of energy with occupation number at the frontier orbitals. So this is exactly the quantity that relate to the Yannick theorem. So then the conclusion is that chemical potential will be equal to the eigenvalue, either constant eigenvalue or general constant eigenvalue. And then the eigenvalue is directly related to chemical potential, and in particular relate to ionization at electron affinity. No statement having been ever made in terms of LUMO, the meaning of LUMO in a constant calculation. But here we have exactly the proof that they are just as meaningful as HOMO, describing electron addition. So Hartree-Fock theory, then you can reinterpret the result as a Hartree-Fock approximation to the chemical potential. That's the HOMO of Hartree-Fock or the LUMO of Hartree-Fock. So this is very different from Kupperman theorem, but very different, same conclusion, but very different meaning. Okay, so conclude the HOMO density, HOMO energy is the chemical potential for taking electron away. LUMO is the chemical potential for electron addition, and fundamental gap is related to the constant gap or the general constant gap. And then, however, that sounds too good, because then why don't we get the good result out of the HOMO and LUMO? Well, DFT has error, systematic errors. So if this is the exact line, the PPLB line, the black one, approximate functional actually behave convex, has this red line behavior. So this convex deviation is that at integer seem to be well approximate the experiment. However, at fraction, at half electron, it is much lower in energy. So this means that the DFT functional violate the degeneracy requirement in quantum mechanics. And it doesn't, the underlying Schrödinger equation has been violated, the linearity has been violated. So this error is very significant. And you can, if you take the chemical potential estimate, it will underestimate ionization energy and overestimate electron affinity, because the chemical potential don't have the wrong slope. So then the orbital from the gap will be give you too small gap I minus A will be too small. In a different direction, Hartree-Fock actually add in a different way, the opposite way, and then the gap is too large. And that's all being observed in any system calculation for atoms all the way to bulk. The eigenvalue from CONSEM are too small, producing the gap too small. It also has a very profound consequence on the charge distributions, because this lowering of the fractional charge systems means it's wrong will bias an answer towards that answer and violate the degeneracy requirement. So if you take two molecules and add the electrons, the electron will, for a functional with convex deviation, it will sit here with half electrons. We'll get a localized answer because the localized answer is high in energy. Or if you have a Hartree-Fock theory, like concave deviation, then it will have localized answer. But the true answer is degenerate. It doesn't matter, it's the same energy. So basically, the DFT has an intrinsic error for too low energy for the localized distributions. So we call this localization error for the concave, and then for convex deviation, the localization error. And that's the commonly seen in most functionals, including GGA, hybrid functionals. And the consequence, it will predict too low energy for delocalized distribution and give too delocalized charge distribution when it has a chance. And you can, there's also another very long list of problems that relate to this. Reaction barrier, overestimate of conductance, band gap too small, and certain those other reaction has wrong energy. So these all, and dissociation of molecular molecules, they all relate to this delocalization error, this mathematical origin. The dissociation, take a dissociation system, H2 plus. If it's one electron, Hartree-Fock will be exact. This is the potential energy curve. Different DFT describe equilibrium reasonably, but when it stretches to large distance, it has a huge error. And this is all because this functional describes the half electron at the dissociation limit too low, energy too low. Okay. So this what we learn is that for the H2 plus dissociation curve, we see a failure of DFT. We don't know what's wrong. But when we analyze in terms of fractional charge, we know what is wrong with the functional mathematically, and it is systematically. And so that's the hope, is that we can use that information to build corrections. You can also see the charge distribution if you calculate chloride in water, and you see that actually the negative charge spread everywhere except in chlorine atom, because spreading tiny fraction to different water molecule lower the total energy. Okay. So all this big long list is all because of this fractional charge system error, systematic error in functionals. Okay. So we have summarized our understanding in this review, in chemical review. Then we wanted to use the knowledge to correct, of course. That's the ultimate goal, to get better functionals. So, and I want to show you why it's so hard. This is a very non-trivial question, non-trivial challenge. So at H2 plus, take this example. At equilibrium, we have good functional behavior, and we wanted to keep that, because at large distance, we have very long energy. So the error and correction are known in terms of fractional charge. We know at limit, infinity, but the fractional charge are not defined. Where are the fractional charge in the system? You only have one electron in the one occupied orbital. You always have integer number of electrons in the calculation. So the fractional variable that we need is not available in a calculation. Second challenge. The correction should be here and should taper down and should be zero at equilibrium, because equilibrium with the fractional analysis is not useful. it shows there's not much error. So what correction we need it at large distance, but we want to get away at small distance. And so that takes many years and many different direction. And we finally we have a theory that published 2018 that we call localized orbital scaling correction. They're able to provide a size consistent correction and systematic improvement on most of the things, that the errors, and then that leads to the optical the excited state study. So what a key quantity that we have to use is called orbitals. It's a normal localized orbital. It's so we use this orbitals set of orthogonal localized orbital to represent the density matrix, and this lambda ij is the projection of the matrix on the localized orbital density matrix, and this relates to the occupation number of the localized orbital. And the localized orbital are linear combination, unitary combination of canonical orbital. The really key element in this is this linear combination span occupied as well as unoccupied space, and it has two parts. One is localized in energy, and other is restriction in an energy window. So we don't allow the completely sum of the entire spectrum. In a later piece of work, we developed a more elegant and better formulation for the energy localization. It's just the spread, the second moment in the position and second moment in the energy, the orbital energy. So this spread, minimize this spread is a restriction. So this becomes really the energy and space localization combined. And for example, you take a benzene molecule when you stretch to very large distance, it's like atomic orbital. So this localized orbital has capability to change according to geometry. At equilibrium, it looks like canonical orbital. So it can become, it depends on, and the reason is because the energy system has gap. And the reason we do this is that because we identify what the difference between here and at large distance is the gap. There's no gap at separation infinity, and there's a significant gap when you bind. So the energy gap is the key. So when we don't have the, when you sum over all the orbital, there's there's no gap, then there's less gap, then you sum over all the localized orbital and you get very, very localized. But when you have a large gap, then you only combine the occupied orbital. So this looks like canonical orbital. So it both span occupied in virtual space and localized both in physical space and in energy space. So very different from traditional localized orbital, only localized in space, physical space, or canonical orbital, which is perfectly localized in energy space and delocalized in physical space. So this orbitals allow us to capture the fractional, what we need. At equilibrium, the occupation will be 1 and 0. When you separate out, it will be half and half. And because separate out is like atomic orbitals. So, and it's all within the same formulation. And so the energy is that you take the occupation number and take a quadratic correction. So it's very simple energy expression. And we have an approximate expression for the curvature, for the second order derivative in terms of localized orbital densities. And this total energy correction add to any functional, then we also have to add correction to orbital energies. So this correction is very easy to, it's less expensive than hybrid functional because you don't have exchange. Okay, so what we can achieve is can showcase in here a helium cluster. That's a theoretical model, which from one helium atom to all the way to infinite number of helium atoms. But interesting thing is that the helium are non-interacting, so they are large distance apart from each other. So we have two measures of the accuracy. You can calculate ionization energy by finite difference, or you can calculate by chemical potential using the HOMO. So then this difference between these two will be the error here. You can see you have huge error between in all the different functionals, LDA or B3 lip. For the finite difference, the eigenvalue is basically wrong. But the bottom panel is the ionization energy calculated by finite difference compared to experiment. See, for one helium atom, the finite difference is really incredible, very accurate compared to experiment. So the error is in the orbitals. But when you have two helium atoms, then the error shifts. So both the finite difference is not as good. The orbital also has a significant error in energy. This trend should continue until you reach to bulk systems where the E versus N line is perfectly linear, but that doesn't mean it does not have delocalization error. It's just show up in the finite difference. And the finite difference is huge in error. So this delocalization error has a size-dependent manifestation. And lOSC, we just add on correction to LDA, able to capture the one helium atom all the way to many helium atoms in the infinity number extrapolation. So that is very challenging task. Okay, then on the practical matter for G2 set of ionization and electron affinity, we can see that this is the original LDA prediction for I and A. And now with the lOSC, we take away the schematic error, and it's all lying on this corrected curve now. We didn't correct all the details error, but the systematic deviation have been corrected. Band gap for polymers has also have exactly the same picture. So this is the N and the polyacetylene. Yeah. So you can see that LDA predict a small gap vanishing at a very large distance, and then the lOSC correction match well with experiment and whereas PT2 for finite system, and it's get a finite gap. Polyacene, same story. So we can predict the gap very nicely now. And the charge distribution, the chloride in water also solved if we carry out the self-constriction calculation. So this is the correct lOSC on PBE compared to CCSD or PBE itself, which is completely wrong. Actually, you have a wrong sign. B3 lip with hybrid functional give you halfway right only. The connection to excited state is developed in this paper. We use DFT to approximate quasi-particle energy and then excitation energy. So quasi-particle energy, as we said, is the ionization energy or electron affinity that to excited states, including the ground state of N and N-1, but also to the excited states as well. So this M index can be excited states. And that can be derived, can be obtained from Dyson equation. But the Komsem equation look very different. But the HOMO and LUMO are already identified theoretically as the functional approximation to I and A are the two quasi-particle energies. And we have plenty of good evidence. This is ionization energy electron affinity for many, many systems. We have this lOSC prediction really compare well to experiment and compare with the best of the GW, the self-constriction GW calculation. So that really we can provide much improvement from the density functional approximation and then get to the accurate as GW, as the best GW, or even better. So with HOMO-LUMO, approximate quasi-particle energy, we'll just extend that to the rest of the orbital energy, the Komsem orbital energy, and make the rest of quasi-particle energy. That's the extension we're making. There's currently no rigorous theory for that. The extension result is very good, just as good as HOMO and LUMO. If you take the ionization energy from experiment of this molecule, naphthalene, lOSC predict the ionization, the highest ionized, lowest IP, and then the rest of the IP as good. The accuracy is 0.37. The original B-lip, of course, is wrong by 3 eV. And across different molecules, we observe exactly the same thing. The approximation for hormone LUMO is persistent for all the other lower ionization energy. And then that means that the constant value really predict quasi-particle energy. So we can then use that to calculate photoemission spectrum. So this is experiment photoemission spectrum. And then we look at all the calculation from lOSC, GW. This is self-consistent GW and density functional original. So the lOSC prediction are comparable or better than GW calculation. This we have this molecule, and we have really many molecules. They have like tens of molecule, very complicated structure, exactly the same conclusion. I'm not going to go over. Well, looking one more time on the quasi-particle energy. The quasi-particle energy is describing an energy add to an excited state of n+1, or energy taking away from a n-1 system excited states. So that means that the ground state information orbital contain excited state information. So this leads to us to the method called QE-DFT, quasi-particle energy from DFT for excitation energy from n-1 ground state calculation. So while we can take one electron away, and then the LUMO will describe the ground state, the above LUMO will describe the excited states. So the difference between the orbital energy, just the LUMO and then the above LUMO, will give you the excitation energy. If you have exact quasi-particle energy, then it will be exact. But with DFT calculation, approximate functional, you get approximate. And so how good is this approximation? This is first triplet, second triplet, first singlet, and second singlet. And the result is pretty good. Very good. The amazing thing is that actually we use, if you don't change the loss correction, use DFT by itself, it's also very good. And the reason is that at low lying states, I think the delocalization error does not cancel out, because when you compare two states very close in energy, the delocalization error cancel out. And however, it's not true for Weber states. This is a Weber states. B-lip will give you very bad Weber states in energy, but lOSC B-lip will get you very good Weber states, because lOSC we corrected the delocalization error. And then charge transfer. This definitely need the lOSC correction, and it has the we proved that it has the calculated, it has the 1/r dependence, corrected dependence. Okay, so we can then study excited state energy surface and conical intersection. You can see that the surface look just as good as TD B3 lip, and the one incredible thing is that it describes conical intersection, while the B3 lip fail. B3 lip will fail describe the conical intersection, and the QE-DFT, which is much simpler calculation. All calculations are done in one shot, one state of n-1 electrons. Then you get all the information for excited states, many excited states. Okay. The last example that I'm coming to is then this was made possible because the truly correct self-consistent calculation we have recently developed, and this is developed last year. This self-consistent calculation, previously our self-consistent calculation has an approximation. The Hamiltonian was not exact, and therefore the approximation leads to really, for difficult case, we cannot converge. But now we have the exact Hamiltonian, can do self-consistent calculation exactly just like the regular functional. So then you can see that I'll show you an example of this, and then come to the last example. So lithium fluoride is a molecule that we look at its dissociation energy. So the energy, binding energy, and if you take a DFT, a B-lip, it will dissociate to partially charged atoms and wrong energy, too low energy. That's the localization error right here. If you use a post SCF, just use the DFT density and do the post correction, not post SCF correction, we get wrong energy in the wrong way. So the blue. So, but if we do the proper self-consistent loss, beautifully, it's set on the right limit, exactly. And you can see that charge, the charge is wrong. The charge on the DFT calculation, regular DFT is very wrong. And it has a wrong charge at infinity. And the loss correctly. I see my time is running up, and this is my last example. The last example is a charge transfer complex, donor acceptor, the donor and the acceptor. And we study the distance as it varies and want to look at the energy, charge, and energy level alignment. So molecular charge, of course, the DFT is belief is wrong. Self-consistent loss give you correct answers. The energy too, perhaps the same story, but the most interesting part is the energy level. At infinity separation, the donor ionization energy must be the experimental ionization energy of the 60. So this is a black dot here. That's where we know the answer. And if you look at different functional calculation from GW, this is the GW and GW, EV-GW, eigenvalue self-consistent GW, actually very good. And self-consistent loss also very good. Just by calculate isolate donor, it's very good. DFA belief is wrong. And if we do post, we don't get the right answer. Okay, so this is the separate infinity. But when you study, it comes in to find a distance 10 angstrom to 2 angstrom, this lined up. Okay, so G0W0 has wrong answer because the density is wrong, and it has an underestimate across entire binding energy. Sorry. Across inside ion binding energy. But the loss GeV corrected. So the eigenvalue EV-GW has the right answer. But on the acceptor side, the electron affinity, the story changed. This is the experimental answer, and the EV-GW failed. So EV-GW failed quite significantly because it cannot line up correctly. So even at 10 angstrom, this blue one it's not approaching the dissociation limit, while the true answer should be, but it's wrong. So it's completely wrong lined up. When you calculate isolated, it's fine. But when you combine system calculation, is wrong. So whatever eigenvalue self-consistent or self-consistent or G0W0 is wrong. The energy level are all completely wrong in this binding systems. And only self-consistent loss because we have the correct density and we are able to align properly. So that's the last example, energy alignment in charge transfer system. So what I've shown you is that we understand some of the key systematic error and we correct it, and we are able to get the reward of photoemission, photoexcitation spectrum, and then energy level alignment in charge transfer interfaces. Okay, thank you very much.
Thank you, Weitao. And we can't virtually clap all for you, so I'll clap. And so thank you very much. I think I'll follow the same strategy as yesterday, which is I'll start with the questions, and we have a few minutes for questions. I will ask some of the questions from the chat, and I'll just read them out. So the first question is from Gabrielle Davino, and it's about the helium clusters. And Gabrielle asks, so these are van der Waals systems, and so the ionization potential should be affected both by the delocalization and the screening or polarization of the different atoms. And she's wondering if that means that your corrected Kohn-Sham scheme can describe screening without charging the system.
Very good question. I think our example, our calculation didn't answer that question. We separate the helium to be so far apart and with vacuum in between, so there's really no screening in the system. So what we are looking at is a pure effect of the localization error. And when you have a finite distance, then of course the screening will come up, and then the very complicated many-body. But then where do we get the experimental comparison? We don't have a benchmark. So we are trying to do the precise calculation so that we know with precise benchmark. And I think what your question is really good case to study.
Thank you. And then next question is from Giacomo Londi, asking how does lOSC compare with range-separated hybrid functionals for the calculations of IPs and EAs?
Yeah, very good question. I think range-separate is very interesting example. Normally you will use the long-range Hartree-Fock in the functional, and for finite systems, I emphasize for finite system, it worked very well. For very small system, when you get to a certain size, it will be trouble because the long-range Hartree-Fock is the incorrect limit for bulk, because that will give you too big a gap. For 100% of long-range Hartree-Fock give you too big a gap for bulk. So I think long-range range-separate does not have the systematic correction as the lOSC has on size and on systems.
Thanks. And then I think for time reasons, this will probably be the last question. So that question is, and this is from Oleg Karlanov, are the localization, delocalization errors you're discussing related in any way to the self-interaction errors in DFT functionals?
Oh, very good question. Can I show a slide?
Sure.
Oh, I don't know. Can you see my slide still?
It's a blank screen right now.
Oh my goodness! Then I don't know how to go.
Now we've got the beginning of the presentation.
Oh, okay. So I have one slide actually addressing that. Because it is a very important question. It is two different aspects, but self-interaction correction is only, I couldn't find it. Maybe I can. I'm sorry, I'm not going to look for it. I have I can send that slide to the person who asked question, but I will answer the following way. Self-interaction error is a very important concept in DFT. It was developed by Purdue and Zonger in 1982 or 83. And what it's saying is that for one electron system, the functional has correlation energy as electron interaction plus correlation and Coulomb doesn't cancel out, not giving you 0. So for one electron error, the electron interaction energy is not 0, and that's the self-interaction error. They're very well defined, of course. But for more than one electron, what is the self-interaction? You cannot define it. For one electron is perfectly defined for any one electron system, but for many electrons, no. And for many years, from 82 up to the early 2000, the whole community thought the self-interaction error is the source of systematic error for all the problem. And I was a big believer, and so we worked very hard to try to find a functional that's self-interaction free. And 2006 was the turning point. Axel Becker has a functional called B203. And we have a functional with Paula and Maurice Sanchez and Cohen called NCY2 functional. Both functional developed completely differently, but both functional are exact for any one electron systems. So it's self-interaction free, error free. So we thought we solved all the problem, but it turned out when we go through all the tests, it solved nearly none of the problem except the reaction barrier improvement. the rest of the behavior, the schematic error of DFT persists in these function nodes. So that's I got a wake up call. So self-interaction error is not the reason, and that's why we developed the delocalization error concept.
All right. Well, thank you very much. You can unshare screen to make room for the next speaker. And I'll say, Weitao, you have a few other questions in the chat. If you end up having time afterwards, I'm sure some folks would appreciate